Welcome back. We're here on day 3 of 12. This is a continuation of yesterday's discussion on SID chips on the Commodore Christmas music and other topics in and around it, not the least of which is analog synthesis and computer music. So here's the agenda for today, but this is demo day. To start with, I'll have a quick play of the original, not the original, but the FoeniXmas at Christmas 23 demo that I created about a week ago. I put it together over the course of 4 days, and I sent it out to the community on Christmas Eve around 11:30 p.m. I barely made it in time, and I'll talk tomorrow about how I was helped along to get this thing done on time. But I'm gonna show you that I have it on the SD card. We're going to be using a F256K today. I do most of my development work on Junior upstairs, but I'm downstairs, so I have access to the K. I have something to tell you about it as well, which is kind of interesting. It has to do with audio. So that's the first thing we're going to do. I'll try and be brief. I'm not going to run the entire soundtrack. You may be tired of hearing it by now. But the second demo is the demo of the work in progress guru mode, as I call it. And this is essentially the same program as the Christmas demo, except I strip away the graphics and I start to put a bunch of stuff on the screen. And what it does is to tie together all the data that we've been kind of looking at in painstaking detail and make some sense of it with a program on the screen. So you can kind of see and hear for yourself as the registers change, as data gets pumped into the SID chip, as time moves forward. And we'll talk about time and other aspects of music probably tomorrow or on the 5th day. But that's what today's about. I'm going to talk a little bit about graphics, but not a lot today. So let me get myself set up here. I'll be right back. Okay, in case you couldn't tell, that was a piece of paper taped to the screen, and now we're looking at the screen. So as I mentioned, I have the F256K here. This is the keyboard model, integrated model. I want to tell you something about the audio specifically before I get started here. And that's the FPGA-based Gideon instances, the 2 SID instances built into the FPGA, which I think was part of Gideon is, I guess, a person who created these things in the first place. It's a core that was created, and Stephanie's leveraging it in the K model. I have to tell you that it sounds better than the SID chips that I bought aftermarket. I'm not going to tell you what brand they were. I don't want to call any of them out for being better or worse than others. But I bought I think 4 of them so far, and I like them. I mean, they sound great. I'm not a SID purist, but I at least want to mention that there's a certain part of this Commodore demo uses sync, oscillator sync, which we've not spoken about yet. And this, hands down, it sounds much better on the K. I was kind of surprised by that. Of course, I haven't tried it against a real SID. There'd probably be a difference, maybe, but there's definitely a difference between the aftermarket, third-party SID chip that I bought and the ones that are built into the instances in the FPGA inside of this K. So that's a positive thing. Let me quickly load up the Christmas demo. I'll talk about the basic program briefly, and then I'll run it and you can see what it looks like. This is for people who haven't seen it, because maybe they don't have a Phoenix, and I didn't make a video of this prior. It's really not a big deal, but I got it working, and there's a little bit of graphics I'd like to talk about. So give me one moment. Okay, it's loaded and it's complete. I'm going to list it out now, and this is the loader is written in BASIC. There are 4 parts to this demo. There's a basic loader. There's the machine language portion, which includes all of the SID data. There's a graphic file, which is, you'll see on the screen. It's a 320 by 240 pixel by 256 color bitmap that I downloaded off the internet somewhere. And then there's the palette, which sits behind the color bitmap that makes it look the way it does. Without the palette, of course, it'd be a mess, because no system would know how to place pixels and how to establish 24-bit color for each of the pixels on the screen. I'll talk about that in just a moment as well. So this is the basic part of the program. It's pretty straightforward. I'm just going to walk you through this real quick. Line 50 clears the screen, of course. Line 60 basically clears the bitmap screen and enables bitmap mode. It then prints on the screen that it's loading graphic assets in binary code. It B-loads, which is a binary load of christmastree.fbmp into 10,000 hex. But the next thing that happens is one of the most important things here, which is load palette. That's on line 110. And that loads the color palette into place. And there's a number of gyrations that need to be kind of run through from lines 10,000 up through 10,070, which is his procedure. And this code, by the way, was written by Ernesto. I pulled it out of one of his programs, as I always do with his programs. He's been a great help, and I've leveraged a lot of his basic work. So this is the program. It loads the bitmap, it establishes the palette, and it displays it on the screen. Then it calls, finally, after it loads the binary, it calls hexadecimal 3000. So I'll run this now and see what happens. It'll take a moment to read in the bitmap. So the bitmap is about 70-something K in size. So if you think about it, we got a 64K machine here. We're loading over 70K of one image. And now you can see it. So I'll turn the music down in a moment. But this is the demo. Essentially, the BASIC is responsible for setting up the palette, as I said, loading the bitmap and enabling it. And you're looking at it here. It then calls hexadecimal 3000, which is my code. And what that does is put some text on the screen. It talks about how to control the player, and it's pretty straightforward. You can either press a key 1 to 7 to play a specific song, or it'll just roll and play one at a time from beginning to end. The entire demo is about 4 minutes long, 4.5 minutes, just like the Commodore demo was. And you can pause it by putting spacebar. If you wait around enough, 8 seconds will go by and that last tone will fade away. And right arrow chooses the next song, and you can speed it up, slow it down, etc. So that's the demo, and these are the Commodore Christmas songs verbatim. This is the data we've been looking at. So I'm going to turn this volume down. Actually, I'm going to turn it off, and we'll reset this, and I'll talk about the latest version of code, which is what I'm really here to talk about today. So remember the back for the text on the screen here, because you'll be seeing it again on a black screen in just a moment. Okay, I'm going to load this up with a slash hyphen, which is the pexec loader, and then the name of the file, which is SIDplay .pgz. Sorry, pgx. No quotes are needed, and I'll bring it right up here. There we go. So I'll pause this, and I want to point out a couple things on the screen real quick. The first thing is, I love telemetry. I love data. This is like a dream come true for me, this project, and it sounds corny, but I just really like making sense of data, doing stuff with it, presenting it in useful ways. So I've got more to do on this, certainly, but I'm pretty happy with how it's come along so far. I want to start with the, well, let's talk about controls real quick. Same controls as before. You can press 1 to 7 to play a single song, and it'll pause at the end. You press the space bar to pause and resume, and you press A to play all of the songs in rotation. Now, I may have mentioned it before, I may not have. I'll be posting this code in a GitHub repo at some point once I'm done with it and have a chance to make sure it's clean and commented well enough. So feel free to jump on there. I'll post it on I'll probably advertise it, so to speak, in the newsletter, and I'll update the description in a couple of these videos, probably for the playlist, so you can find out where it is if you come back to the video. And I'm hopeful that a lot of the routines in here are useful to other people. So I'll talk more about code in kind of the second half of this, but I at least wanted to mention that if I had not mentioned it previously. So you can see the player's paused. It's playing the song Good Christian, and you've got a bunch of numbers on the screen, hexadecimal numbers. So to begin with, you'll see right below the now playing, it says mem pointer, and it says 4A75. So that's the hexadecimal address of where the SID data lives in memory. If you recall yesterday and the day before, episodes 1, episodes 2, I kind of tortured you a bit, walking you through in painstaking detail how the SID data is laid out in bytes, what each of the hex codes meant, what the data means roughly in some cases. In some cases, it didn't mean anything to us. This player now, with this mode active, it gives you a better chance of understanding it. And the mem pointer will change dynamically as the program moves forward. So every phrase, as we spoke about, every phrase returns back to a main loop, which is the event handler, and it updates a lot of these numbers. So to start with, I'm going to roll it just so you can see it moving. So it'll kind of jump ahead, and you may notice that when the song's over, it'll jump to a different part of memory. It may jump to like 6 something, or may jump back to 3 something. So they're not necessarily consecutive, but certainly each song's consecutive. The song will end when it hits a hexadecimal EF, if you remember that. That was at the end of the long listing. And as I mentioned, and as I've done, I posted the Rudolph the Red-Nosed Reindeer song on the Phoenix marketplace. So you see it just switched to a new song now. Okay, the next thing to talk about is the time sequence on the right. There's 3 hex digits there. None of them represent length or well, one represents tempo, but not in the usual sense. The number 5/8 is the amount of time, it's a time delay actually, between the beginning of the playing of the first phrase and the point at which it would otherwise return back to the basic program in the Commodore program. In my program, it's 100% assembly language, but I had to simulate the way that their algorithm worked somehow, and I estimated it, and I used some of their data, and I rounded it up, and I timed it, and I went around in circles with this. But the point is that, as we'll talk about probably the day after tomorrow, Commodore executes a graphic update every time a phrase comes back. And you may notice that, say, Frosty the Snowman dancing with the children is in tune with the music. The Christmas lights on the tree is in tune with the music. Santa Claus you don't necessarily know so much as he's coming across, but the snow is in tune with the music. And that's because, or in time with the music, that's because the Commodore version of the original demo would wait in a for next loop, believe it or not, for a certain value, and then it would execute the graphic instruction. Then it would return back and have a second delay, which was represented by the second digit there, 0F in this song. And then it would loop around again and start again. So it's a really weird setup. I'm emulating it in assembly language, and there's a built-in delay, a significant delay that I had to throw in the middle of it. I'll talk more about this when I talk about timing. But the F9 on the right is the default time. I'm going to probably enable kind of like a slider with a sprite to depict that visually. But I can go down to slow down the machine, so to speak. And I'm going to go down, I think we're down to E0. Let's see. E2, E1, E0. Yeah, I'm at the bottom. So you'll see how slowly now the mem pointers are increasing. 050, F, 1D, 29. And those are actually bytes that's going phrase to phrase to phrase down the sheet. So that's kind of the slowest it'll go. You can press the left arrow key to get back to the default, which is F9. There you go. Now it's moving quite quickly again at regular song speed. Each song has a different time that it runs at. So the 44.2C is specific for Frosty the Snowman. When it moves on to the Commodore song, it'll, I don't know what it's going to be honest. I don't have it memorized, but it's appropriate for that song, and it runs roughly the same time as the original did. 70F. Okay. When we talk about time as well, we'll talk about beats per minute and how it kind of maps to this system that Commodore invented with this first kind of Christmas demo. Finally, under time where it says PC, that's actually phrase counter. So that will increase from 0 when the song starts over again. It increases from 0 upwards. Then we'll get up to the 90s, the A's, B's, C's, depending upon the length of the song. We'll see what this one is probably going to end soon. A, B, let's see, which one? Oh, this is the longest song actually of them all. It goes to C something. CD. So I got nervous when I was writing it that I might have to put a 16-bit number in there and deal with that, but I didn't have to. It fit within one byte. So anyway, moving along now. You'll notice from left to right, we've got voices. And I'll probably step over to, you won't be able to hear me as well. Actually, I'll annotate it on the screen when I edit this down. You'll see voices V1, V2, and V3. And you'll notice that it says C0 hashtag or octothorpe or pound sign, depending on what part of the world you're from, which is intended to be the musical note. Haven't gotten that part done yet. Then it's got the waveform. So you'll notice the waveforms are pulse, sawtooth, and sawtooth. Well, that's going to change. It changes by song, and it changes in the middle of the song. It's kind of interesting to see when it changes, to see when the people that developed the music have an oscillator with no waveform at all, because that happens in a couple sequences here. And I'm told that it's possible to have multiple waveforms selected at the same time, at least on a spec sheet. I mean, you can have a triangle plus a pulse wave, for instance, and have a compound waveform. Analog synthesizers do support this. I haven't seen it, and I haven't been in and around the SID scene much, but my algorithm concatenates a string with all the settings that are selected within what's called the control register. We'll talk about that in a little bit. I'll probably save that for another day because it is going to be quite lengthy discussion. I like to get the right graphics on the screen. So voice 1, voice 2, voice 3, they're separated by colons, and then you'll see on the right is the filter amp section, which, as I explained yesterday, applies to the entire synthesizer, so to speak. So now moving down into one of the voices, we'll talk about voice 1. You'll see the FRQ, that's the frequency. So those numbers, let me slow the tempo way down again. Go down to the bottom. As each note's played, and you can see each update is essentially a note being played, you'll see the frequency change sometimes. 4822. If I were to look up 4822 on one of those charts, 8C, see, that was a very quick note. E316, D61C, these would map directly to a musical note. And I have to establish a table in my code so I can print that on the screen. That'll be right next to the pulse, the waveform display. So that's what the left column is. The frequency applies to each of the three voices. The second one is pulse width. If the oscillator is using a pulse width, there's probably a width established in this field. It's a 16-bit value. It's 9A01 here for this particular song. I'm not sure it's going to change. It may not change. But one technique, and I alluded to it yesterday, a technique of 80 synths, which was very big at the time, was something called pulse width modulation. What that is choosing a pulse width that's variable and altered by a low frequency oscillator, kind of a second oscillator, would do nothing but increase and decrease the pulse width. If you remember yesterday, I showed the Mini Moog has on its panel 3 fixed widths for the pulse. The Commodore 64 does not. It has a variable width, and it can be anything. I think it's a 12-bit number. It's an 8-bit number, I believe. It's a single byte, and then there's another there's another nibble. So it's pretty broad. And one technique to really make a really interesting sound is to alter, while the oscillator is playing, alter the waveform by messing with this register, which is pulse width. Moving to the right one more, the CR is the control register. This is a control register for this voice, and you notice it's toggling back and forth from 40 to 41. The 4 represents pulse wave, and the 1 represents the gate on and 0 is gate off. So you can watch it, and I don't have it playing right now, but at some point I'll put high quality audio in with this display, and at some point I'll have the display tracking down the screen. I'm still yet to do that, so that's kind of the next step for me. So in any case, this is interesting. Look right now, voice 1 has nothing. Voice 2 is saw, voice 3 is saw. And this is frosty. Now voice 1 is pulse. So it kicked up. The beginning of the song doesn't have any use of the first oscillator. At a certain point it comes in. It's very interesting to listen to and to watch the numbers, especially at a very slow rate. And of course there's a single step mode I mentioned, which we'll get into next time. Moving on to the right, and by the way, the ring modulator, the sync capability, the ability to disable the oscillator, and what's the and then the gate are all in the second nibble of the control register. So that's the 1 and 0 that's flipping back and forth. When it gets to the Commodore song, which is next, the Bach song, you'll see some things happening that haven't happened yet on any of the other 6 songs, and that's the use of sync across the oscillators in different ways. So let's see, I talked about, I guess from left to right, everything having to do with a voice. Second voice is the same, third voice is the same, and then finally we talked about the filter and amp section, which includes largely filter controls, but also kind of the VCA, or the voltage controlled amplifier section. Of course, here it's not a voltage controlled amplifier, it's a digitally controlled amplifier, but it's essentially just the loudness. That's what we're talking about here. So the right half of the right nibble, or rather I should say it a different way, the right nibble of the last byte on the right, which is 1F right now, the F, otherwise known as 15 or 16 because we're counting from 0, represents the volume. That's about as loud as it'll get. The rest of that byte, or those bytes, and the cutoff bytes represent the frequency cutoff, represent the amount of resonance, represent the type of filter, etc. So we're displaying the information here. We're not decoding it. I may get to that. But in any case, you can see it changing as the tunes change. So here's now that song, that Commodore song. You can see voice 2 has pulse and it's synced to a different oscillator. And you'll see it switch around, right? These will change waveforms mid-song, which is very interesting. And again, I'll have probably another day high quality output audio kind of tracking. I'm also going to have the bytes and the time tracking down the screen, so it'll scroll downward as each of the kind of sequences move forward. So hopefully that was a quick enough overview. I'm trying to make this a little bit quicker than yesterday. I got out of control yesterday with a 40-minute video. This one looks like it's going to be around 15 or 18. So I'm going to stop there. Covered quite a bit in some fast talking. Hopefully this has been interesting to you. It'll get more interesting as time moves forward, but at least so far I've been pleased with the way it's been moving along, and we'll catch up again tomorrow.